Hi everybody, welcome back to Statistics. Today we're in section 6.1 and we're going to be talking about discrete random variables. So this section is going to be a big turning point for us. We started out the course talking about descriptive statistics and then we talked about probability. But remember, the goal of statistics is to be able to use statistics taken from a sample plus probability, put them together and be able to draw conclusions about the larger population. So this section is where we first start to be able to put things together. So in this section we will talk about distinguishing between discrete and continuous random variables. We will learn to identify discrete probability distributions and how to graph them. I'll also show you how to calculate and interpret the mean of a discrete random variable, and we'll also talk about expected value. So that's a lot to get in one lesson, so let's go ahead and get started. Now imagine a probability experiment with me. Suppose we flip a coin 2 times. The sample space would be heads heads, heads tails, tails heads, or tails tails. Those are the only 4 possible outcomes. Now imagine that instead of caring about the actual outcome like heads tails or tails heads, suppose we're only interested in the number of heads. For example, we might want to know if flipping the coin twice yields 0, 1, or 2 heads. So now we're not so concerned with the actual outcome as we are with the number of heads, and the results of our probability experiment are now numbers. When the outcome of a probability experiment is a numerical result, we call that a random variable. A random variable is just a numerical measure of the outcome from a probability experiment, and its value is determined by chance. Random variables are often denoted using capital letters like capital X, and in our coin flipping example, if the random variable capital X represents the number of heads in 2 flips of a coin, then the possible values of X, in other words the sample space of X, is lowercase x equals 0, 1, or 2. Now notice that capital X represents our random variable, but lowercase x represents the individual outcomes of that random variable. So now there are 2 types of random variables. There are discrete random variables and continuous random variables. We're going to be working with discrete random variables in this section, but in the later chapters we'll talk about continuous random variables. So first of all, a discrete random variable has either a finite or countable number of values. The values of a discrete random variable can be plotted on a number line with space between each point. And I'm sure you remember talking about discrete data and continuous data back in chapter 1. So the difference between discrete and continuous is the same here. With discrete numbers, you jump from one value to the next. So 0, 1, 2, 3, 4, all of those are possible values, but the values in between those whole numbers are not possible. So that's discrete. And then a continuous random variable has infinitely many values possible. The values of a continuous random variable can be plotted on a line in an uninterrupted fashion. So where the discrete random variable had to jump from one value to the next, with the continuous variable, any value would be possible. Now let's look at example 1. So it says determine whether the following random variables are discrete or continuous and state possible values for the random variable. So our first scenario is the number of A's earned in a section of statistics with 15 students enrolled. So the number of A's earned could be anywhere between 0 and 15, but it can't be anything between the whole numbers. For example, the number of A's can't be 2.6 or 3.8. The number of A's has to be either 0 or 1 or 2 or 3, all the way up to 15. So we'll say that this is discrete, and the possible values are all the whole numbers from 0 all the way up to and including 15. Now for part B, the number of cars that travel through a McDonald's drive-thru in the next hour. Well, we don't know how many cars, but we do know it would have to be a whole number. So it's possible that 0 cars could drive through. Not likely, but possible. It's possible that only 1 car could drive through. And we really don't have any way to tell the maximum number of cars that could drive through, but we can tell that this is not a continuous variable because we know it's not possible for a fractional number of cars to drive through. So we need to say that this is discrete, and the possible values are all the whole numbers from 0 up. And then part C, the speed of the next car that passes a state trooper. Well, remember that one difference between discrete and continuous is that continuous data is measured where discrete data is counted. We measure speed, so we know that that's continuous. Let's go ahead and say that this is going to be a continuous random variable, and the possible values are any number greater than 0, because a car traveling 0 miles per hour could never pass the state trooper. It would be sitting still. So now that we know what a discrete random variable is, we can get another definition. A probability distribution of a discrete random variable x provides the possible values of the random variable and their corresponding probabilities. So I think we've seen probability models before. This is just going to be a probability model, but for a discrete random variable. Also, a probability distribution can be in the form of a table or a graph or a mathematical formula. We have seen them before as tables, and remember they look a lot like a relative frequency distribution. So here's example 2. It says, suppose we ask a basketball player to shoot 3 free throws. Let the random variable capital X represent the number of shots made. So lowercase x is 0, 1, 2, or 3. In other words, capital X represents the random variable number of baskets made, and lowercase x then is all the possible outcomes of that random variable. If he's shooting 3 free throws at a time, it's possible for him to make 0 of them, 1 of them, 2, or 3 of them. And the table shows the probability distribution. So the possible outcomes for number of baskets made are 0, 1, 2, or 3. So for each set of 3 free throws that he makes, the probability that he'll make 0 baskets is 0.01. The probability that he'll make 1 basket of the 3 is 0.10. The probability that he'll make 2 baskets out of the 3 is 0.38. And the probability that he'll make all 3 baskets is 0.51. So notice that since these are all the possibilities, the probabilities add up to 1, because one of these outcomes is certain to happen if the player throws 3 free throws. Now here are the rules for a discrete probability distribution. Pretty much the sum of all probabilities has to equal 1, and each probability for each outcome has to be somewhere between 0 and 1. We can't have a probability that's negative or a probability that's more than 1. So here we have 3 tables, and let's look at each one and decide whether each one is a possible discrete probability distribution. Okay, all we need is for the probabilities to add up to 1 and each of the probabilities to be between 0 and 1. So here's our first table. The possible outcomes are 1, 2, 3, 4, 5, and here we have the probabilities. But the problem here is that this probability is negative, and so this is not a probability distribution. We know that probability cannot in fact be negative. It has to be between 0 and 1. So this is disqualified as a probability distribution. And on part B, let's look at this table. Again, we have 5 possible outcomes, but here the probabilities, when you add them together, you get a sum that's larger than 1. And the probabilities have to add up to 1. So this is not a probability distribution either. And let's look at the third one. In the third one, all of the probabilities are between 0 and 1, so that's a good thing. And if we add these probabilities together, we'll see that the sum of all the probabilities is 1. So we can say for certain that this is a valid probability distribution. Now we are going to talk about graphing probability distributions. This is not that different from making a histogram, but it does look a little different. So let's just talk about this for a minute. In the graph of a probability distribution, the horizontal axis corresponds to the values of the random variable, and the vertical axis represents the probability of each value of the random variable. So for our next example, we're going to graph the probability distribution that was given to us in the first example. So remember that on the horizontal axis, we label each of the possible values of the random variable. So I'll go ahead and label this 0, 1, 2, 3. And I did not write a 0, but 0 would be where the two axes cross. And then the probabilities seem to go from 0.01 up to 0.51. So what I'm going to do is start here at 0 and count up by tenths. So I have 0.1, 0.2, 0.3, all the way up to 0.6. And I went a little bit past 0.5 because my largest probability is a little bit more than 0.5. So the probability that he makes 0 baskets in his 3 shots is 0.01. If this is 0.1, then the bar for 0.01 would be very short. I'm just going to put it right there. And the probability that he'll make exactly 1 basket is 0.1. So right here at 1, I need that bar to come up to about here. And the probability that he'll make exactly 2 baskets is 0.38. So that's going to be about here. So the bar for 2 will come up almost to 0.4. And then the probability that he'll make exactly 3 baskets is 0.51. So the bar for 3 will come up to a little bit past 0.5. And that's what our probability distribution graphs look like for a discrete random variable. Now remember some of the things we talked about back when we were learning about histograms. We learned that to describe the distribution of a variable, we describe its center, its spread, and its shape. And the graphing calculator can help us with all 3 of these. So consider the following data set, which represents the number of people living in 10 randomly sampled houses. In the first house, there were 2 people, then in the second house, 4 people, then 6, 6, 4, 4, 2, 3, 5, 5. It would be very easy for us to find the mean of these numbers. In fact, I'm sure you can do it with no trouble. Add the numbers and divide by 10, and the mean of this data set is 4.1. Now let's turn this data into a probability distribution. So we'll say that our random variable x is the number of people living in each house, and therefore our possible outcomes are 2, 3, 4, 5, and 6. And then we'll need to tally up the frequency of each outcome. So there's a 2, a 4, 2 6s, 2 more 4s, another 2, a 3, and 2 5s. So our frequencies are 2, 1, 3, 2, and 2. And now to make the probability distribution, we divide each of these frequencies by the sum of the frequencies. So now notice I'll label them x and probability of x. So the outcomes are the same, and 2 divided by 10 is 0.2, 1 divided by 10 is 0.1, then 0.3, 0.2, and 0.2. Here is our finished probability distribution. Now we're about to talk about how to calculate the mean of a discrete random variable. And what we usually have in front of us is the probability distribution for that discrete random variable. We hardly ever have the actual raw data. So for the last data set we were working with, I've put the raw data here with the probability distribution. And I want to show you something. A common mistake a lot of people make is that when they're trying to find the mean of a probability distribution, what they think they can do is just average the numbers in the x column. And if you average these 5 numbers, you'll see that the mean is 4. But we know the mean of our raw data was 4.1, not 4. So the probabilities have to come into play somehow. What has to happen is that we have to weight each value by its relative frequency or probability and then sum all the products. Now if you remember section 3.3, this probably sounds very familiar to you And in fact, we will use the same process to find the mean of a probability distribution that we used to find a weighted average in section 3.3. So the formula for the mean of a discrete random variable should look very familiar to you. It's just the sum of the product of each outcome times that outcome's probability. So here is the formula for the mean of a discrete random variable. The mean of a discrete random variable is given by the formula mu sub capital X, because this is going to be the mean of the random variable, is equal to the sum of the product of each possible outcome and its probability. So what you have to do is take each outcome, multiply it by its probability, then add all of those products together, and that's the mean of your random variable. Now we can also use the calculator to find the mean and the standard deviation of a probability distribution. And you probably remember how we did it in section 3.3. This is going to be the same procedure that we used for finding the mean of grouped data or for doing weighted averages. Now when we do this on the calculator, you'll notice that sample standard deviation is not available. That's because the calculator knows that the numbers in list 2 add up to 1. So it knows that we are working with a probability distribution, not a sample, so it treats it like a population. And we will have population standard deviation available to us, so that's what we'll use. So here's example 6, and you see that they've given us the table from example 2, where we had the basketball player who was asked to shoot groups of 3 free throws each. And it says use the calculator to find the mean of the probability distribution. Now what I've done is I've gone ahead and entered my X values in list 1, and I've gone ahead and entered the probabilities in list 2. So what's about to happen is that we're going to get the calculator to average the numbers in list 1, but using the weights that it finds in list 2. We know that he makes all 3 free throws a lot more often than he makes 0 of the free throws. So we need the 3 to be weighted at 51%, while the 0 is only weighted at 1%. So now all we have to do is click Stat, arrow over to Calc, and you may remember this again from section 3.3. And we want to do one variable stats. This is the new operating system where I'm going to tell the calculator that my list is list 1, but my frequencies are in list 2. And even though they're probabilities, it will still work. So now I can just arrow down to calculate and press enter. And there is the mean of our probability distribution. And you would actually round this to 2.4 because our outcomes had 0 decimal places. Therefore, our mean should have 1 decimal place. So we would round this to 2.4. And now let me just remind you how it looks with the old operating system. So if you have the old operating system and you press Stat, Calc, one variable stats, now it does not offer you that little wizard screen that we saw with the new operating system. You have to know to tell it that you want to average the numbers in list 1, comma, but you need it to use the frequencies in list 2. So one variable stats, list 1, comma, list 2. Then you can press enter and you get the same results screen that we got with the newer operating system. Now here we have a table that contains the raw data for 100 trials of this experiment. So the basketball player took the basketball and made 100 trials of 3 free throws each. And what you're seeing here is that on the first set of 3 free throws, he made all 3 baskets. On the second time, he only got 2 of the 3. On the third time, he made all 3. And so on until the 100th time, he made all 3. Now, if we were to actually average all 100 of these numbers, we would see that the mean of this raw data is 2.35, and that's very close to the mean of the probability distribution that we found with the calculator just a minute ago. In fact, if we were to let the basketball player continue making trials of 3 free throws each, then the more trials he makes, the closer we expect the mean of this raw data to get to the mean of the probability distribution that we found with the calculator because of the law of large numbers. Here's another example. This says, in the following probability distribution, the random variable x represents the number of activities a parent of a 6th to 8th grade student is involved in. And they want us to first verify that this is a discrete probability distribution. So in order for this to be a probability distribution, we need each probability to be between 0 and 1, and we do have that. And we also need for the sum of all these probabilities to be 1. And if we add all 5 of these numbers together, we see that the sum is 1. So this is a valid probability distribution. Now in part B, they ask us to graph the probability distribution. So we need our horizontal axis labeled with numbers 0 through 4. And for the vertical axis, we'll look at our probabilities, and we see that the largest probability is 0.322. So I need my vertical axis to go up at least that far. I chose to count by tenths up to 0.4 and then go back and put the halfway mark in between each pair of tick marks. Now notice that we have here 3 decimal places, and on a little hand-drawn graph, we're never going to be able to be that exact, but we can just get as close as we can. The bar for 0 should go up to 0.073. So I see here that I have a tick mark for 0.05 and a tick mark for 0.1. So the bar for 0.073 is going to go somewhere in between there, about halfway. And then the bar for 0.117, well, 0.117 is somewhere between 0.1 and 0.15. So just slightly higher than 0.1. And then the bar for 2 is going to be 0.258. So 0.258 is just slightly more than 0.25. And then the bar for 3 is 0.322. So that's going to be about halfway between 0.3 and 0.35. And then the bar for 4 is 0.23. That's going to be about halfway between 0.2 and 0.25. And there is the graph of our probability distribution. Now for part C, it says compute and interpret the mean of the random variable x. So to find the mean of this probability distribution, I've pulled up my calculator and I've already entered the x values in list 1 and I've entered the probabilities in list 2. And so now I'm going to say stat, calc, one variable stats, and it already has list 1 and list 2. Remember, if you're on the old operating system, you need to tell it list 1, comma, list 2. So now I'll have it calculate. And the mean of this probability distribution is 2.519. Now since our outcomes are whole numbers, we'll just round the mean to 1 decimal place. That's 1 more decimal place than the outcomes had. So we'll say the mean is about 2.5. And now to interpret the mean, what does it mean to say that the mean of this probability distribution is 2.5? Well, it means that on average, parents of 6th through 8th graders are involved in about 2.5 activities each. Now part D says compute the standard deviation of the random variable. We do have a formula for standard deviation of a probability distribution, but we are not going to use that formula ourselves. So we'll just rely on the calculator functions for this. So notice that on the same screen where I was when I calculated the mean, the line for sample standard deviation is blank. That's because the calculator knows we have a probability distribution because the sum of the probabilities is 1. Therefore, it does not treat this like a sample, it only treats it like a population. So it's telling us the population standard deviation rounds to about 1.2. And now part E, same probability distribution. What's the probability that a randomly selected student has a parent involved in 3 activities? Okay, well we can see here that for 3 activities the probability is 0.322. So we can say the probability that the random variable equals 3 is 0.322. And then part F, what is the probability that a randomly selected student has a parent involved in 3 or 4 activities? So of course the word or is telling us to add these. So the probability that a parent is involved in 3 or 4 activities is going to be 0.322 plus 0.230, and that comes to a sum of 0.552. And part G, what is the probability that a randomly selected student has a parent involved in fewer than 3 activities? Okay, well, fewer than 3 could be 0 or 1 or 2, but it could not be 3 because it says fewer than 3, so we don't want to include the 3. So the probability that a randomly selected student has a parent involved in fewer than 3 activities would be 0.073 plus 0.117 plus 0.258 for a total probability of 0.448. Now I do want to point out, in case you have a large probability distribution with lots of lines, so lots of different probabilities to add together, you always can be on the lookout for a chance to use the complement rule. So the probability that our random variable has a value less than 3 is the complement of the probability that it has a value of 3 or more. So we could just say 1 minus 0.552 because that's the sum of these two numbers. 1 minus 0.552 would also give us 0.448. So you can add the 3 numbers or you can subtract the other 2 numbers from 1. It's up to you, but I just want you to be on the lookout for chances to use your complement rule because sometimes that can save you quite a bit of time. Now the mean of a probability distribution is also called the expected value. Expected value is just another name for mean. If the experiment is performed repeatedly, then over the long term we should expect the mean of all the outcomes to approach the expected value. In fact, that's why it's called the expected value. We can expect the mean of our trials to match the mean of the probability distribution in the long run. That's the law of large numbers at work again. So you'll find that very frequently expected value problems in textbooks involve money. So here's a good one, I think. This says a term life insurance policy will pay a beneficiary a certain sum of money upon the death of the policyholder. These policies have premiums that must be paid annually. Suppose an 18-year-old male buys a $250,000 one-year term life insurance policy for $350. According to the National Vital Statistics Report, the probability that the male will survive the year is 0.998937. Compute the expected value of this policy to the insurance company. Now remember, the expected value is just the mean of the probability distribution. And also notice that they asked us to find the expected value of this policy to the insurance company. So when we write the numbers down, we need to do it thinking about what the insurance company has to gain or lose. Now there are only 2 outcomes for this 18-year-old male. Either he lives through the year or he dies. And so we'll make a probability distribution out of this. The way we are going to decide what goes in this column is what is each condition worth to the insurance company. And the way I like to do it is I think of money coming in as positive and money going out as negative. So it kind of works the same way your checking account would work. So let's say that if the 18-year-old male lives, then the insurance company has gained his premium. He paid the premium and they didn't have to pay out anything, so they gain $350. But if the 18-year-old male dies, he will have paid his premium for the year, but they will lose $250,000. So how much money are they actually out? To find that, we're going to say negative $250,000 plus $350, and that is negative $249,650. So what this amount is how much the insurance company is out if he dies, and then this number is how much they gain if he lives. Now the probability that this 18-year-old male lives is actually 0.998937, so virtually certain that he's going to live. But the probability that he dies is the complement of 0.998937. So 1 minus 0.998937 is 0.001063. Now you can put these numbers in your calculator as a probability distribution. These numbers would go in list 1, and these numbers would go in list 2, and then find the mean of the probability distribution, and you'll see that the mean here is 84.25, and it's positive, so that means the company can expect a profit of $84.25 for each one of these policies that they sell to an 18-year-old male. And here's another expected value problem for us, and this one is a gambling problem. This one says, in the game of roulette, a player can place a $5 bet on the number 17 and have a 1 in 38 probability of winning. If the metal ball lands on 17, the player wins $175 and they get back the $5 they paid to play the game. Otherwise, the casino keeps the player's $5. What's the expected value of the game to the player? And if you play the game 1,000 times, how much can you expect to lose? Okay, well, there are two possibilities here. Either the ball lands on 17 or it doesn't. And so now let's figure out the possible outcomes for our random variable. If the ball lands on 17, then it says the player wins $175 and they get back their $5. So the player actually has come out ahead $175. If the ball does not land on 17, they've just lost their $5. So we'll put -5 there for that. Now the probability that this player is going to win is 1 out of 38, so 1/38. But the probability that he's not going to win is 37 out of 38. So 1 chance that he wins and 37 chances that he loses. And now you can use your calculator to find this mean. Now when you do get into the list editor in your calculator and you go to put your numbers in list 2, you really can put it in just like this. Just say 1 divided by 38 and 37 divided by 38. There is absolutely no need to convert these into decimal form before you put them in the list. Let the calculator take care of that, and that way you're not doing any rounding. So if we did put these in the calculator and find the mean of the probability distribution, we would see that mu is approximately -0.26, and that means that a player can expect to lose on average 26 cents per game. Now, if the player played the game 1,000 times, he would win some and he would lose some, but he can expect that on average he loses about 26 cents per game. So 1,000 times -0.26 means that he's going to lose approximately $260 if he plays 1,000 games of roulette. And here's one more example that's a lottery problem. This one says, in the Cash 5 lottery in Connecticut, a player pays $1 for a single ticket with 5 numbers. 5 balls numbered 1 through 35 are randomly chosen from a bin without replacement. If all 5 numbers on a player's ticket match the 5 chosen, the player wins $100,000. The probability of this occurring is 1 out of 324,632. If 4 numbers match, the player wins $300. This occurs with a probability of 1 out of 2,164. If 3 numbers match, the player wins $10. This occurs with a probability of 1 out of 75. Compute and interpret the expected value of the game from the player's point of view. Okay, there are a few different things that can happen here. The player can match all 5 numbers, or 4 numbers, or 3 numbers, or they lose. So let's go ahead and write that down. They can match 5 numbers, or 4 numbers, or 3 numbers, or the player loses. Now let's see if we can figure out the value of each outcome. If the player matches 5 numbers, then they're going to win $100,000, but they paid $1 for a ticket. So that is a gain to the player of $99,999. If the player matches 4 numbers, they're going to win $300, but again, they paid $1 for a ticket, so that's a gain to the player of $299. If the player matches 3 numbers, they're going to win $10, but again, they paid $1 for a ticket, so that's a gain of $9. If the player loses, they're only out $1, so that's going to be -1. Now let's write in the probabilities. The probability that the player matches all 5 numbers, they told us, is 1 over 324,632. The probability that they match 4 numbers is 1 over 2,164. The probability that they match 3 numbers is 1 over 75. And the probability that they lose is everything else. So they did not tell us the probability that the player loses, but it's obviously the complement of these probabilities. The complement of winning the game is losing the game. So to calculate the probability that the player loses, I'm going to say 1 minus the probability that they match all 5 numbers, minus the probability that they match all 4, minus the probability that they match all 3. Everything else ought to be the probability that they lose. Now we're not going to be able to get a fraction for this without doing a whole lot of work because this denominator is very, very large. But we can get a decimal approximation and that will be fine. So if you add this up on the calculator, you'll get a probability that the player loses equal to approximately 0.9862. Now if you'll go ahead and enter these numbers in list 1 and list 2 of your calculators and find the mean of this probability distribution, you'll see that the expected value is approximately -0.42, which means that in the long run the player can expect to lose an average of 42 cents per ticket. So I find these expected value problems very interesting because I want you to see that the casinos always have the game fixed. They're not cheating. They're just playing a game where the odds are in their favor. So the price of losing is very small to you, but the probability that you'll lose is very large. On the other hand, the benefit of winning is very large, but the probability that you'll win is very small. And the casinos and the lotteries know what these probabilities are, so they're able to set the prices here so that they come out ahead. Remember, somebody could go to the casino and get lucky once or twice. Somebody could buy a lottery ticket and get lucky once or twice, but you cannot use lottery tickets as an investment strategy because in the long run, it just doesn't pay off. If it did pay off in the long run, the lotteries and the casinos could not afford to stay in business.